All right. Hey, Honors Chemistry. So I wanted to continue these video notes for Unit 3 important information on quantifying energy. So it's the one that starts on this. We are going to jump to page 10. In the previous videos, I walked you through the new equations of Q equals mc delta T and Q equals mH. We did two very simple examples of just plugging and chugging those equations with given information. Now we're just going to up it a notch and do a couple of things with these equations. So let's do an example where now instead of doing one of each, we have both things occurring of a temperature change and a phase change. So it says a can of soda at room temperature, 25 degrees Celsius, is poured onto a cold block. Over time, the soda that was poured onto the rock begins to freeze. The final temperature of the frozen solid is -8 degrees Celsius. Assuming the heat capacity and the freezing point of the soda is the same as water, calculate the change in thermal energy of the soda initially from room to zero. A can of soda is 12 ounces. I'm going to actually change this from room to -8 degrees Celsius. So I want like this whole change. Okay? So to solve this problem, we're going to have to keep track of what kind of energy is going to be involved because we will use both Q equals mc delta T and Q equals mH. All right, so let's draw a cooling curve for soda, which is going to end up being the same as water. We're going to make a note that 0 is going to be very important for us here. So it says it starts at 25 degrees Celsius. So I'm going to be like right down here. If I'm at like 25 degrees Celsius, let's just say that's 25 degrees Celsius, it cools, and then eventually something's going to happen. It hits 0 and freezes, and then it goes to -8, which I'm going to say is right here. Okay? So as you can see, I'm going to have three different segments here, and let's label them. This segment where I go from 25 degrees Celsius to 0, that's going to tap into thermal energy. And I have a change in temperature. So Q equals mc delta T is going to happen here. Then I'm going to have phase energy. Delta T is going to be equal to 0. So I'm going to need to use Q equals mH because I'm going to have a phase change. And then after that phase change occurs, I'm going to have a different substance, I'm going to have a different state of matter now, change temperature again from 0 degrees Celsius to -8 degrees Celsius. So that's going to be another change in temperature, which is going to be Q equals mc delta T. This is tapping into thermal energy. So I have three things happening here. This is a bit of an involved problem. I have three things happening. I have my soda cooling, and then my soda freezing, and then my frozen soda cooling again. And so each of these are going to have their own Q's. Okay? So the way that I could calculate Q total is going to be Q of 1 plus Q2 plus Q3. 1, 2, 3. I'm going to have to add all these Q's together. And then I don't want you to forget that M for everything is going to be 340 grams. C for liquid water is 4.18 joules per grams degrees Celsius. C for solid water is different. It's 2.1 joules per grams degrees Celsius. And then the H for freezing is going to be -334 joules per grams. Okay? So keep that in mind, that these are going to be values that I'm going to use. All right, so let's calculate Q1, which is going from 25 degrees Celsius to 0 degrees Celsius. So if I want to do this calculation of 25 to 0, my M is 340 grams. My C, it's a liquid. At 25, this soda is a liquid. 4.18 joules per grams degree Celsius. And my delta T is T final minus T initial. My final temperature is 0. My initial temperature is 25. 0 minus 25 is negative 25 degrees Celsius. So now I could plug this in. I'll do 340 grams, 4.18 joules per grams degrees Celsius, and negative 25 degrees Celsius. To cool it from 25 to 0, multiplying all of this together, I get 340 times 4.18 times negative 25. I get negative 35530 joules. That's just for this first segment. So right here, this is requiring negative 35530 joules. Let's do Q2. Q2 is associated with a phase change. Q2 is associated with this phase change here. I'm freezing. All right, so my mass is still going to be 340 grams. My H of freezing, I already told you up here, and we got that before, these are constant, is negative 334 joules per gram. So now all I'm doing is plugging into Q equals MH. So there's no change in temperature. So 340 grams, and then negative 334 joules per gram. And we actually got this in our last video. This requires negative 113,560 joules. And that number is going to be associated with freezing right here. So I'm going to put that there. 113,560 joules. Right? So this segment is losing over 113,000 joules. This segment is losing over 35,000 joules. These two are two different segments. To cool it from 25 to 0, losing this much. To freeze it, this much. And then after it freezes, it cools again. But guess what phase it is here now? It's a solid here. So Q3 is going from 0 degrees Celsius to negative 8 degrees Celsius as a solid. So M is going to be equal to 340 grams. Conservation of matter, this mass is the same. I'm not gaining or losing mass, and I should not. So it's the same mass. C is going to be of the solid this time. So 2.1 joules per grams degrees Celsius. And then delta T is going to be T final minus T initial. Final is negative 8. Initial is 0. This is going to be equal to negative 8 degrees Celsius. Okay? And so now I have MC delta T. I can calculate that. 340 grams. 2.1 joules per grams degrees Celsius. Negative 8 degrees Celsius. And I'm going to get another number here. So 340 times 2.1 times negative 8. And I get negative 5,712 joules. And that's going to be associated with this line down here. This is going to be negative 5,712 joules. Now, if I want the total energy, guess what I'm doing with these three numbers? I'm going to add all of them together. And I'm going to try and squish this down at the bottom here. Q total is going to be equal to negative 35530 joules plus negative 113,560 joules plus negative 5,712 joules. I should get a large number here. I get negative 3, 5, 5, 3, 0, plus negative 1, 1, 3, 5, 6, 0, plus negative 5, 7, 1, 2. I get negative 154,802 joules. This is the total energy lost. Okay? So to recap, if I'm doing more than one thing, if I'm changing temperature and changing phase, I need to add up those energies separately. In our previous page and our previous notes, we had two separate questions. But what if I had combined example 1 and 2 and said, oh, it went from 42 and then it went to 0 and froze? I would just add up these two sections together. Okay? So in conclusion, to help you kind of organize this, I would use a cooling or a heating curve and keep track. Okay? And if I'm ever on a curve where the line is angled, I'm using Q equals MC delta T. If I'm ever on the curve where it's flat, I'm using Q equals MH. Okay? Let's try and look at another example. What if I gave you energy? Okay? So example 4, what if energy is given in the question? And this is kind of easy. Question 5 is going to be a bit difficult. So what if I gave you 1,000 joules and I said this energy was removed from 100 grams of liquid water at 75 degrees Celsius? What is the final temperature of the water? Right? So I'm looking for a final temperature. And I told you, assume no phase change has occurred. So if no phase change has occurred, and I'm having a change in temperature, I'm going to be using this equation, right? I have a change in temperature. Because I told you what's the final temperature, and I'm removing energy. So I'm going to be using Q equals MC delta T. Well, I gave you Q. It's 1,000 joules. The M is 100 grams. It's a liquid. It's liquid water. So C is 4.18 joules per grams degrees Celsius. The only thing I don't have is delta T. Now, I have an initial temperature, but I don't have a final temperature, and I'll show you how to do that later. But don't forget that delta T is T final minus T initial. So delta T, I don't know. So let's plug these numbers in. Q equals MC delta T. 1,000 joules is equal to 100 grams. 4.18 joules per grams degrees Celsius. Delta T is my unknown. If I'm solving a problem like this, this would be like if I were to solve a problem and I'm like, 20 is equal to 5 times 1 times x. 20 equals 5x. How would I solve for x? Well, you're going to tell me that I divide both sides by 5, right? I have to move this 5 away from the x. Well, in this situation, my delta T is like my x. So I'm going to have to move these two things on this side. Well, if you don't want to do that all together, I'm going to multiply these two things together so I could combine terms. Grams and grams are going to cancel out. I'm going to be left with 418 joules per degree Celsius times degrees Celsius. Okay, and now I want to get delta T by itself, so I'm going to divide both sides by 418. So divide both sides by 418. And I'm just bringing over these units of joules per degree Celsius. I'm going to be ending up with degree Celsius. 100, now I have 100 over 14 is going to be equal to delta T. Delta T... 1,000 over 418. And I get and I'm just going to round it to 3 sig figs for right now. Or I'm just going to put 3 places. I'm not doing sig figs, so don't worry about it right now. 2.39 degrees Celsius. So now I just got that my delta T is equal to 2.39, and it's positive. Positive 2.39. I'm removing this, though. Okay? So I'm removing energy. So something that I did not keep in mind, the reason why I'm putting this as positive is because I said I removed energy. That means that this 1,000 should have been negative. And now I have a negative delta T. So first I just showed it to you how you would probably do it just by plugging and chugging, but you have to look out for keywords. If it says removed energy means delta T is going to be equal to negative. It means the joules is going to be negative. My minus sign here means negative. So my delta T is negative 2.39. Now over here on the top here, I said delta T is equal to T final minus T initial. Well, I just solved that my delta T is negative 2.39 degrees Celsius. I don't know what my T final is. I'm looking for it, but I do know that my T initial is 75. So T final minus 75 degrees Celsius is going to be equal to my delta T. So if I want to solve for T final, just like if I were to solve a problem, what if I said 8 is equal to x minus 5? How would I solve that? I add 5 to both sides. X is going to be equal to 13. But in this case, if I have x is going to be T final, I'm going to have to add 75 to both sides. Which means T final is going to be equal to negative 2.3 plus 75. 75 plus negative 2.39, and I get 72.61 degrees Celsius. Final temperature is 72.61 degrees Celsius. Now, does this make sense? Well, oops, I just knocked over things. Does this make sense? Well, it says that energy is being removed from my water. If I remove energy, I should decrease in temperature. Did I decrease in temperature? Yup. I went from 75 to 72.61. Okay? I'm going to end our video notes here. On Monday or the next time we meet or for later, I'm going to start before you do worksheet number 3 with example number 5. Example number 5 is going to be quite difficult. It's going to be the one that comes from your worksheet. We're going to do example number 5, and then we're going to jump over to worksheet number 3. Okay? Alrighty. Make sure you take these video notes and you have these ready for me when I come back.